In the years around 1580, in the city of Florence, Italy, in the home of Giovanni de' Bardi, Count of Vernio, a group of people came together to solve a common problem. They called themselves the Florentine Camerata. Their mission? To reform modern music. What Vincenzo Galilei, father of Galileo, member of the Camerata, called corrupt and incomprehensible contemporary music, according to Wikipedia at one point in time. That music was polyphony, and it sounded like this. Polyphony has 4 to 6 melodies, all intertwined, all equally important, and it conveys a feeling of holiness. But the Camerata, they wanted something more. The Camerata dared to ask the revolutionary question, what if we could understand the words? Specifically, they wanted to find a balance of words and music to maximally convey emotion, and emotions other than just holiness. So they did this. The Camerata met over a series of months and years, and I'm kind of fascinated by them because they remind me of a modern agile team in many ways. So they were a multidisciplinary group. There are musicians and poets, but also artists and scientists and clergymen and philosophers and all the people who are really thinking about what's going on in the world and how can we improve it. They had sponsorship, so they met in the homes of Giovanni de' Bardi and also Jacopo Corsi. In some ways, it's more like a meetup than a team, but let's work with it. They had that common purpose to reform music, and they had agreed upon methods. So they wanted to bring back the way the ancient Greeks wedded words and music. Because back then they thought history went in a circle as opposed to a spiral of progression. And so backwards was forwards was backwards. Now there's some disagreement among musicologists because it's not like they had recordings of the ancient Greeks. So maybe this was just a way to lend legitimacy to their work and they didn't really care. So it's kind of like when I cite computer science papers from the 1970s. That's okay. What matters was they agreed on how they were going to approach this in a lot of ways. And so they met and they talked, and Barty's son was like, dude, they get together for hours and hours, and nobody gambles and nobody drinks. Caccini, one of the singers, remarked, I've learned more from their learned discussion than from 30 years of descant. Now, descant, I had to look that one up. That means lecturing. So what you're getting now. Fortunately, there's the whole rest of the conference for learned discussions. They didn't just talk, though. They did play music, so it functioned as a workshop, and they experimented with the music that they wrote, and they played it together. And then they had code review. So I find it interesting that the censors who were criticizing the performance were nominated for the occasion. They were appointed to that role. It wasn't just that asshole who hates you and takes it out on your code. They didn't all get along, though. There was some rivalry between the two chief sponsors, and Corsi wanted to do more playing of music, and Bardi wanted to do more talking about it, but these balanced. And similarly with the musical stars, Perry and Caccini, Perry was like, it's about the words with some music, and Caccini's like, it's about the music with some words. Well, but with that, they did achieve balance, and they succeeded. The Camerata totally changed history. They invented the stile representativo, which led to opera. It's called monody now, and it's this radical idea of a single melody with a little bit of musical accompaniment. Everything that's now obvious wasn't always. This was new at the time. So here's a sample of one of the earliest operas we still have a record of from Monteverdi, influenced by the Camerata.
Nubi, barbari nubi, che rompe, verno, pallido abitator, la di cui mano, abita delle morti.
Now, I still can't understand the words, but that's because I don't speak Italian, and I'm told that if you do speak Italian, it doesn't help, because that's ancient Italian. So it would be like if I was singing Chaucer or something. But back in the day, they really did understand the words, and they understood the story, and people got the emotions that the composers and lyricists were trying to convey. And whole reams and reams of people, whole new portions of society became involved with music and excited about music. The Camerata really did change the world. But that's not what I find most interesting. What I find most interesting about the Camerata was how it changed them, the people in the Camerata. So here, from Wikipedia, are some of the publications put out by individuals from the Camerata after 1600. So there's operas here, yes, but there's also poetry, there's philosophy, there's scientific treatises, there's mathematics. The individuals in the Camerata went on to do great things individually. These aren't even half of the Camerata members who have Wikipedia articles today. They didn't expect that in 16th century Florence. So something was magical there. And this doesn't happen only in music. This is a pattern, and it's a pattern observed by Dr. Ruth Katz. So when I went to investigate the Camerata and learn more about them, I found this paper in the Journal of the History of Ideas, which is really cool. And it compares the work of the Camerata to collective problem solving in science. So in science, it's a recognized phenomenon to have a kind of invisible college, a community of learning behind great advances. So we like to give Nobel Prizes to one or two people. We like to think of discovery as an event that happened to a person. But what have they been doing before that? Who are they talking to? Who works in their lab? Who did they correspond with? Who criticized earlier, worse versions of that idea to lead to the good ones? Like Ben Franklin is a great example. Ben Franklin discovered electricity. But he was building on the work of dozens of amateur electricians. Science was an amateur game back then. Electricians from around the world who all corresponded. And every failed experiment that he knew about was part of his successful ones. And he just happened to be the one that hit upon the theory that worked the best out of all of them, but he did not do that alone. That invisible college is that group of people who share a common purpose that they work on both separately and together, and they go back and forth working on that. Invisible colleges have some characteristics. One is tacit understandings of appropriate methods of research. So they kind of have some process compatibility. And then priority problems, that means fighting over who was first. More on that later. And finally, they have a shorthand communication. They acquire a shared language by talking to each other, which then makes it easier for them to communicate, which builds more of a shared language. And that makes them closer and more effective. One of my favorite camaradas in science, or invisible colleges, is the Club of Honest Whigs. So now we're up to like 1770 maybe. And they met fortnightly in the London Coffee House, which is in London. And they met to imbibe and dine and discuss science, especially electricity, but not only, and religion and politics. And you've got a diverse group of big thinkers here. So Franklin's in this group, but also Joseph Priestley. So this comes out of a book called The Invention of Air about Joseph Priestley, because he's credited with the discovery of oxygen, which he didn't do much with, but he passed that to Lavoisier, who, chemistry. Priestley was very free with his ideas. He also invented the carbonated beverage and passed that to somebody who made a lot of money off of it. He also, and this was not recognized at the time, but I think his most important discovery was, okay, so he puts a plant in a jar, a sealed jar, and he finds out how long it takes to die. And then he puts a mouse in a jar, and he finds out how long it takes to die. A lot of mice were sacrificed for this. And then he puts the mouse and the plant in the same jar, and he observes that they didn't die nearly as soon. So he figured out the cycle, or noticed anyway, the cycle of oxygen, carbon dioxide, and that wasn't recognized as crucial until like the 1920s and 30s when ecology became a thing. So Priestley accomplished a lot, and part of that was due to his participation in this group. Now, one more thing about the coffee house bit here. So this is the Enlightenment, and the Enlightenment is a time of great advancement in human progress. And one of the reasons behind that is it's right after the part where coffee has started being imported into all of Europe, and people have switched to drinking coffee with breakfast instead of beer. And they all got smarter. Every discipline is new again, and whole new disciplines emerged. Right, so this also happens in art, this kind of invisible college camarada thing. You can think back to the salons in Paris. So now we're in, the 1880s and on up through the 19th century. And Dr. Katz remarks on the coffee houses where you've got critics and artists and dealers, not only painters, but all the stakeholders in the art industry, and they come together to solve a common puzzle. Now in art, the common puzzle corresponds to an artistic style. For instance, Impressionism solves the puzzle of how do I paint not what is, but what I see. And they work together in these coffee houses. Here's one of them. So this is a terrible picture because I took it, but that's fine. I got to go to Montmartre and take this picture, and I'm so happy. And in particular because this salon is called the Agile Bunny, except in French. And that's really cool. And just on the street from this is a plaque on one of the houses in Montmartre, and like these are a bunch of famous painters and printmakers and poets and stuff who lived in that house, this big house, all together around the same time. That's not a coincidence that so many people who were part of this group later became famous and influential and went on to do great things. One of those who lived in this neighborhood was Van Gogh. So this is a painting he painted back in the Netherlands. I think that's a cabbage and some potatoes. There might be a carrot in there, but there's not a lot of orange. So his brother, Theo, is an art dealer in Paris, and Theo writes, and he's like, Vincent, you must come here. You'll never believe the colors these people are using. And then Vincent runs out of rent money and gets evicted, so he does go. And then, he learns about whole new colors and styles, and Theo remarks, you have managed to create for us a circle of artists and friends. And these people, they all like paint each other's portraits, and they have like they push each other, and they develop the style together. And like the paintings of Toulouse-Lautrec and Paul Gauguin, and a generation later show up in the salon of Gertrude Stein. And Gertrude Stein is an author, and she and her brother Leo were American, but they were living in Paris, and they had some money, so they fed a lot of artists. They had an atelier, and every Saturday night, people would come through, and not just artists, but also philosophers and authors and photographers, poets. And she had one of probably the first private collection of modern art, because modern art is just becoming a thing. She introduces Picasso to Matisse, and they have a rivalry going. This is fine. And Picasso, he meets Georges Braque, and together they create Cubism. Cubism solves the puzzle of how do I paint not one perspective, but all the perspectives in the same painting. Now, Picasso is one of the few artists who made money in his lifetime. So then he's running a salon, and these are some of the people who pass through his salon, and those are photographers and philosophers and mathematicians. And another person who came through his salon, another painter, was Alexandra Exter, and she was from Kiev, so she took what she learned back to Kiev and taught it to her friends, these other Alexes, and one of them, Bogomazov, he painted this goat head picture, which is on my bedroom wall today. The ideas, they bigger as you pass them along. They grow. And they grow us as we share them. This also happens in software, like the authors of the Agile Manifesto. They were totally a camerata. And they came together to solve a problem and changed the world, and totally did. And now how many of them have 18 books to their names? Oh, there's so many. And a couple of them are here today. Another of these camaradas that I've observed from going to conferences and meeting a lot of people, and I keep running into people who were in ThoughtWorks London in 2003 or 2006. This is a group of people, multiple clients, but the same consulting company, so they're talking to each other and they're solving the problem of how do we deploy software in under 2 weeks and without breaking everything. And out of that, you get the continuous delivery book, and Jez goes on to write a bunch more stuff about DevOps, but then you've got Dan North, who went on to invent behavior-driven design, among other things. Nat Price is talking about unit testing, and Sam Newman, you may know him as the prophet of microservices. Another one like that is Spring, around the same time, but distributed. So these people solved the problem of how do we write Java Enterprise Edition without stabbing our eyes out? And the Spring framework definitely changed the Java world, and indirectly the rest of the programming world. And now Rod is my CEO at Atomist, and we're busy reinventing software delivery. And the bunch of other people, both business people and programmers, who were at Spring have gone on to start companies and Keynote, QCon, and I keep running into them. I think the evidence is in music, in science, in art, in software. Great teams make great people. You want to hire a bunch of developers, a bunch of great developers, and put them in a room and poof, have a great team. I've not seen that work. But the other way around does. Great teams make great people. So why is that? Because if we understand a model of why, maybe we can take this even farther and get our teams to make us great too. So I have a model of why I think great teams make great people, and I would like to share it with you. It starts with Gregory Bateson. So Gregory Bateson is an anthropologist in like the 40s through the 60s, 70s. And a couple of his camaradas were the Palo Alto School. They developed a model of human communication as shared building of meaning instead of linear transfer. The Macy Cybernetics Conferences was another one. There's a very multidisciplinary group of statisticians and physicists and anthropologists and psychologists and biologists who got together, and they founded the science of cybernetics, which grew into systems thinking. Okay, quick aside about Gregory Bateson. His father was William Bateson. William Bateson was a biologist who coined the term genetics. Because genetics, the work behind that started with Mendel, but Mendel, who did like the bean plant experiments, he didn't have a camerata. So his super important results on the quantization of inheritance languished for a couple decades until William Bateson picked them up. And William Bateson duplicated the experiments. Of course, he didn't do that by himself. He had a lot of help, and he had a lot of help, especially from women in his lab, his wife and other biologists who took an interest in this, because all the male biologists were like, that's not real biology. And genetics, it's real biology now. So, right, William Bateson, genetics. Gregory Bateson, systems thinking. And systems thinking, quick definition, is about, in a lot of our lives, you can't just take a system and break it apart and look at the parts and understand what's going on. The leverage, the strong forces are in the interrelationships and the way the parts impact each other while they're in action. Now, Gregory Bateson's other contribution then is his daughter, Nora Bateson. And Nora Bateson grows up in this dynamic model of communication and this atmosphere of systems thinking, and she takes it farther. She says, look, okay, we've made progress on systems, but that doesn't take it far enough, because it's more than the parts and the way they interact each other. Something more is going on. In the 50s and 60s, dozens of grad students spent hundreds and thousands of hours like cordoning off a square meter of prairie and counting the blades of grass, and dividing the bugs into species and weighing all the different species of insect within square meters of prairie. And they were quite certain that if they just got enough numbers and enough formulas into the computer, they could model the ecosystem and predict outcomes. And it never worked. It never worked because those species are not static from generation to generation. They're always learning from each other. So the parts don't even hold still, and the interrelationships don't hold still. And she said, we need a new word. If you have a living system made of living parts, then it's built on mutual learning between the parts, and they're constantly changing. So she coined a term, symathesy, from the Latin sim together and mathesy learning. And a symathesy is a living system made of living parts based on mutual learning. Kind of like our team. Our teams are more than the sum of their parts. We know that. We know they're also a product of their interrelationships. But more than that, the parts are a product of all of their past interactions with each other, because we're constantly teaching and changing each other as we interact. So that's a symathesy. Our teams are a symathesy. And if we look at a system is not the sum of its parts, that would be an aggregate. Systems thinking adds it's a product of their interactions. And symathesy adds that the parts are a product of past interactions. And that's very, very powerful. There are no zero-sum games in a symathesy. We win together or we lose together, but it's gonna be interesting. Our software team is a symathesy, but I think if there's something crucial and specific to software development that takes this even further and makes it more interesting. Because if I look at my team, and I think beyond the org chart, a team, as I define it, as someone defined it on the internet, and whoever they were very wise, is everyone necessary for me to succeed. And for me, success is impacting the lives of my customers by operating useful software. To do that, I need several other humans, some of whom are near me on the org chart, but I also need that software to be running. The running software itself is necessary for my success, so it's on my team. And the databases and whatever abstraction of hardware I'm thinking about, this is part of my team. And it's part of my symathesy because I learn from it, from the exceptions it throws, from the data it changes, from the bits that actually get used, from the logs. I'm learning from my code. And of course, the code learns from me because I change it. So the running software is in the symathesy. And also our tools, because I don't learn anything from it directly. I have to have a SQL prompt, and I have to have a log window, and I have to get PagerDuty calls in order to learn from it. And similarly, in order to change it, I need my IDE, I need my version control, I need my deploy systems, I need my automated tests. I'm learning from my tools. I can't learn from the software without them. And my tools are learning from me as long as I can change them. I can add automated tests. Hopefully I can improve my build process, and I can query in SQL or in the log aggregation. All of this is my tools improving as I teach them. So all of this is the symathesy. Okay, this explains a couple other things about software development to me. One is why we need to show up to work with our whole selves. Because in order to participate in a living system, we need to be alive in it. Another one is why this is so freaking hard. Because I've been developing software for almost 20 years now, and it has not gotten easier. I mean, I think I've gotten better at it, but it seems like the better I get at it, the harder it is. And I think that's because it really is super complicated. And the more things I can change, the more interrelationships here, the more to keep track of. It's a lot. It wasn't always that way. When I started as a developer, I had my little piece of the system that I was assigned to work on, and I was told what to change about it. If I needed some data, I said, how do we use the database? And they gave me the book on Oracle. And these days, if I don't, it's not that simple, right? These days I say, what database shall we use? And how shall we do the backups? And how shall we do migrations? And what schema shall we design? And oh my gosh. Yeah, there's a lot more options. And there's a lot more to think about. And I think that's kind of a progression as a developer, is as we get good enough at the little parts, our scope kind of broadens and we start to take more and more of the system, of the semathesy, into account, and we're able to have more influence. And if you take this a little farther, you get to the senior developer or high-level individual contributor, or maybe the architect level. These people are thinking about more than just their team system. They're aware of the wider system within the company, and they have relationships both within the team for bonding social capital and outside the team, bridging social capital, both within the company and within the industry. And like at this conference, you can make connections that will then be a source of specialized knowledge at some point that you don't always have access to inside, and that's all important. Another reason that a high-level individual contributor, in order to have a real impact, we need on our team people who have influence within the organization, because a semathesy, any like self-adaptive learning system, necessarily influences its environment. Any species in an ecosystem influences its environment. Any participant in a market is going to have an effect. And on our teams, you can't just say, okay, team, be adaptive and learn within this box. You can say, implement this API, but you can't refuse to change the wider organization. It's sematheses all the way up. The other thing this tells me about senior developers, so if you look at the senior developer as someone who has this kind of breadth of understanding and influence, you can't hire that. Okay, nobody from outside can possibly know your system and have relationships within the company that's necessary to have this kind of impact. Now, you can hire someone who can get there quickly, who can get there within a year by asking the kind of questions: why do we do this? What else changes? Who cares about this stuff? But that's in opposition to hiring someone who will hit the ground running. Because if I want to be productive quickly at a job, I need to narrow my focus to a piece of the system that I can get enough grasp on that I can change it without breaking everything. Whereas if I want to move into a wider position of usefulness, I need to spend more time asking questions and thinking about the broader scope, and that can be paralyzing. I've totally been there. Right, so you can't hire a senior developer, sorry, you have to grow them, but you can look for people, if you want to, who like to ask questions. There's one more thing I need to add to this diagram before we move on. So we'll zoom back in, and there's a concept missing here. The thing is, while we're working within the semathesy, we can talk to each other and we can interact with people, but this team cannot look down and see directly what's going on in their moving software, and they can't change it directly. Until Tron is a thing, we are limited to the representations that we have, to our screens, our keyboards, our buttons, our shell prompts. We're limited by the line of representation. So between the social and technical spaces in this socio-technical system lies the line of representation. And this is everything that gives you visibility or control into the running software. So it can be your code editor, your editor screen, because your code, you can look at it and make predictions about what the software will probably do, and you can change it to have influence, but that needs to go through your version control, and then somewhere there's a deploy button, or at a crudest level, there's SSH, which will let you do anything, which is both great and terrible, but mostly terrible. And then on the other side, you've got your log aggregators and your observability tools like Honeycomb, and your exceptions that come through. Oh, and your SQL prompt, that's a super important one, or whatever database interface you use to look at the data. These are super important. And when you look at this system that's based on mutual learning, you start to see how crucial those points on the lines of representation are, And you can think of like your chat apps interfaces, and you start to realize that your tooling is really important. Your build system, what information does that give you? How does it tell you about the failed test? All of those little interface pieces are really crucial to the learning in this system. And the other thing this means is when you're doing your work of making decisions about how to change the system, you're not operating with it directly. You're not moving objects around on a table. You're working with your mental model of the system. That's how we make decisions. And your mental model, Woods' law says, for every sufficiently complex system, everybody's mental model is necessarily incomplete and out of date. And everyone's mental model is incomplete and out of date in different ways. Now, this is true, but it's also good. I mean, the different ways part is good, because when we're working with a team, we need our mental models to be sufficiently consistent with each other that we can communicate. We need that shared language and understanding, but we need them to be different enough so that between all of us, we have the knowledge we need. The limitation in our work as developers is not how much we can do, it's how much we can know. Because these systems are really complicated. And I can't know everything about how my software system works, and the build and the deployment and the hardware and the blah, blah, blah. And I can't know everything I need to know about security, accessibility, user experience, monitoring, blah, 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 blah. I can't know all of that. And sometimes I feel bad. I listen to these conference talks about all the things that a developer should know. You should build security in from the start. You should build accessibility in from the start and internationalization. And I'm just like, I can't know everything. But that's why we have networks of people. That's why we have our teams. And we don't want to know the same things. We want to know some overlapping so we can communicate, and then different things on our teams. That's really important. But these mental models are super, super crucial because they're how we make decisions, and that's how we implement change in the system. But these mental models, specifically the ones about how the system we're operating on works, are incredibly hard to obtain. And if you think they're hard to obtain, trust me, they're harder. Valentino Breitenberg is a philosopher, and around 1968, he published a book called Vehicles. Little thought experiments of building up very simple vehicles to very complicated ones that look like little animals or act like little animals. And in it, he illustrates very clearly the law of downhill invention, uphill analysis. This says that it is easier to start from a simple system and build it up and build up the complexity and build it up and build it up while building up your mental model of the system at the same time. That is much easier than coming to an existing working complex system and figuring out how it works. This explains why there are so many JavaScript frameworks. Because it is easier to build your own JavaScript framework that does exactly what you want and nothing else. And then gradually you have to add more features, and you add more features, and it's completely obvious to you because you built it and no one else in the world. That is easier, it's not less work, but it's easier than learning React. Despite the millions of hours put in by hundreds and thousands of people for Stack Overflow answers and documentation and books and all the effort it takes to make React possibly mentally accessible to us, that still can't make it easier than the thing you wrote yourself with only the features you need, because that's in your head, and that was easy enough to get in your head. Now, it feels productive to build it yourself because it's more typing, but it's mentally lazy. So not invented here syndrome, mental laziness. Physical industriousness, but just think about that. And then the other thing, once you realize that, then you stop feeling bad for how hard it is. Because it is hard to learn React. I'm trying to make a web app, and oh my gosh, I am such a back-end developer. It's really, really hard. There are a lot of complexities. The front-end world is interesting. It has texture. And React is trying to smooth that out for us, but it really is a hard problem. So don't feel bad that learning a new framework is really hard and that you mess up using it a lot, because those mental models are incredibly, incredibly hard to build. One situation that results from this is illustrated here. Okay, purple developer, he's working on this system down here. Purple developer has a really strong mental model of this system, probably because they wrote it back in the day. And purple developer is chugging along and making changes, but maybe they're bored and they want to move on to something else, or maybe we need even more changes than purple developer can make alone. And so here come blue and green. They've been assigned to this project, probably part-time, and they don't have a mental model of how the system works. I mean, they have some vague ideas. They think they know something about it, but they start digging around the code, and they're like, oh, I'm trying to figure it out. It is perfectly possible, and I've been in this situation multiple times, for purple to be chugging along, implementing stuff and changing this system fast enough that no matter how smart they are, blue and green will never get an understanding of it. They will never build up their mental model because purple can invalidate it faster than they can build it. It is so hard. And meanwhile, purple is like, who are these morons? They can't do anything in under a week and then they screw it all up. Yeah, there's reasons for that. One of these developers looks like a 10x developer. One of these developers is drastically more productive than the teammates. Now, there are multiple kinds of 10x developers, and this is one way to get that status within your organization. But of course, it's not the good way. The good way is to build everyone else up too and 10x your team. But does purple have that incentive? Because what needs to happen here, the solution to this problem, is for purple to take their hands off the keyboard. Do not make any change to that system directly. The only way to make change to that system is through the hands of blue or green or both. So pair programming, or even better, mob programming. And blue and green at the keyboard, and while they're implementing the changes, they get to ask questions. How did you know to do that? How does this fit together? How would you test that? Why did you make this change here? What does this mean? And then that mental model can transfer as you work together on the system. That's the only way I've seen to do this effectively. And it is really effective. But it means stepping back and taking a productivity hit for purple. So is purple rewarded for that? Or is purple rewarded for only their own work with their fingers? And this gets back to those priority problems in an invisible college. Because in science, it's a problem that if they're racing to be first, if the first person to publish a concept is the only one who gets any credit for it, then you get things like Newton and Leibniz are both working on inventing calculus, and they corresponded with each other in cryptic code that they didn't actually want the other person to be able to understand. They just wanted to have said it, but not. It's really bizarre because there was that conflict of, I need to be the first to publish this. And everybody knows Newton, and not many people know Leibniz, poor guy. Because it is. We have this problem of wanting discovery to be attributed to a single person. And while we have that, do we have that in our teams? That's something to ask about your team. Do we attribute accomplishments to a single person or to the group? And do we all get to contribute to that? Because ideas are not conserved like energy. As we share them, they grow, they get bigger. And we want the ideas to grow because we want to grow. When we think about, how do I grow a team? Well, if my team were an aggregate, I would grow it by adding more people. If my team is a system with interrelationships, then I can also look at growing those relationships. Thank you, Agile. That was really helpful. But when I think about it as a symathesis, as a system based on mutual learning, what determines the size of a system like this? Let's look at some other ones. The market is a symathesis, and when we measure the size of the economy, we measure the flow of money, right? So I bought a croissant this morning. If the cafe downstairs uses that to pay their employee, and their employee pays their rent, and then their landlord hires a plumber to fix the toilet, that's like 1, 2, 3, 4. That's like 4 times 350 added to the economy, to the GDP, I should say. So GDP is not a measure of money in the economy, but of flows of money. Similarly, in ecology, when you're looking at, like, you got a fish pond and you're like, oh, how big is this system? How big is this ecosystem? They measure that in terms of flows of carbon or nitrogen or phosphorus, whatever's the limiting nutrient, flows from one species to another. So if you've got your algae getting eaten by the phytoplankton, and then your little minnow eats that, and then your big fish eats the minnow, each of those is a flow of carbon, and they measure that by, like, getting the fish, and they count the fish, and then they, like, I don't know, they burn it or something to find out how much carbon is in it. And so they measure the amount of carbon in each species, and then eventually it gets pooped out to the detritus at the bottom of the pond, and that counts too. So when you want to grow an ecosystem, a growing ecosystem is one with increasing flows. So that could be more carbon is added to the system, it's growing geographically, hypothetically, but it can also be new species are coming in, and the food chain is growing, or there's just more diversity, and the flows are increasing. So in our teams, if we are a symathesy, a system based on mutual learning parts, learning from each other, then what we want to maximize is the flows of mutual learning, including in conversations with each other. We want to learn from each other. Mob programming is the best for this. We've got the whole team working with just one keyboard and one screen. This applies all the knowledge of your team to the single problem at the same time. Plus, you never get merge conflicts. And then our software learns, so when you think about things like back pressure or Kubernetes doing its thing, or it's like, oh, that pod's dead, guess I'll start a new one. These are the software learning what's going on and responding to activity in the other software. And then how does it learn from us? We get better at coding it, but also, we create automated tests, and we create new queries, and we create new points on the line of representation for access to the logs, or new little chat bots that give us access to this. This all increases the flows of mutual learning, especially that line of representation is a key point where a little bit of effort can go a long way to make it easier for you to, like, I don't know, build a dashboard to get the information you need really quickly, to increase the flows of mutual learning. And then just appreciate the learning that people are giving to each other. So when purple developer pairs with blue and green, purple is maximizing mutual learning. Can we reward that in our team? It's really hard to measure, but it's not hard to detect. Because you can ask people, who helped you today? Where did you learn that? Who made that nice error message that just totally fixed my problem for me? You can detect mutual learning in your team and reward it. And the thing is, if you really want to be a great developer, if purple wants to be better, don't sit there looking like a 10x. Actually be a 10x. Help the other people on the team, and purple will grow. Because purple is gonna, well, for one thing, he'll probably learn something from blue and green in the interaction, but also purple gets to go on and do something new. This is one of those oblique goals that you can't hit directly. If you want to be great, put the team first. And if you think you can't hire enough great developers because the talent pool is just too small, we need to relocate to San Francisco, that won't help you, because great developers are not born. They're not trained, especially not self-trained. There's only so much we can get from YouTube. We really need that interaction to pass knowledge and practices around. Great developers are not born, not even in San Francisco. Great developers are symathesized. So create your own by putting the team first. Okay, this is cool and all, but there's one more point that came out of that paper that really shocked me. And it gave me an idea, which is kind of audacious, but also kind of cool, so I want to share it with you. It starts with a bit about the surrounding culture, because the Camerata were right at the end of the Renaissance, like the peak of the Renaissance, and they were right in Florence, in the center of it all, and there was innovation in the air. Side note about the word innovation. in Priestley's day, I learned that the word innovation had negative connotations. It was a dangerous idea. It challenged the existing order. It might disrupt the system. Disrupt was also a negative word back then. So this innovation is in our current use, which is a positive use. Language does change. But the Camerata were just swimming in it. They were swimming in a sea of social and cultural and ideological ideas and practices, all of which contributed to the emergence of opera. One of these was the idea of systematic testing and measurement. They had a new way of thinking about the world. So the scientific method was just beginning to emerge. And Vincenzo Galilei was the first recorded person to study music systematically. Like he strung out a string, he'd put a weight on the end of it to make it tight, to add tension, and he'd go bing, bing, and he'd be like, oh, a C, pretend that's a C. And then he'd string out a little shorter string until he got bing, bing, one octave higher. And then he looked at the ratios of the string lengths between octaves, between notes, between chords. And then he did the same experiment with the tensions in the string. And he found consistent ratios for this. I'm sure that was useful to the Camerata somehow. And then in Priestley's day, it was they had the empiricism during the Enlightenment, so they believed we learn about the world through our senses, and then we can apply reason to what we see to design experiments to test what we think is true about the world. And this idea of like applying rational thought to the world was actually, it was kind of revolutionary. Everything that seems obvious wasn't always. So this is one reason Jefferson and Franklin and Priestley and John Adams, they all intertwined science and religion and politics because of this emphasis on rational thought, they thought maybe we could come up with an innovation that's not bad, an innovation that changes the world for the better. So they had new ways of thinking and changing their world. These days, we have systems thinking, we have complexity theory, we have computers that can think for us. We are smarter. Every discipline is new again, and whole new disciplines emerge from the power of the computer as an extension of our brain. And with these complexity theory and propensities and statistics, and we're really learning how to deal with non-determinism in a more rigorous way, so we can think about systems with fuzzy boundaries that exchange energy with their environment. We can think about systems far from thermodynamic equilibrium, where entropy does not have to decrease all the time. We can build things. Every system that we really live in and interact with, from our teams to our families to our houses, all of these are far, far from thermodynamic equilibrium. So we're learning new ways to think about this, and we can take this farther and make more change. They had the printing press. That probably helped them with their research about the music of the ancient Greeks. We have the internet for maximum knowledge dispersal, but knowledge dispersal is not enough because there's only so much that one person can cram into their head. Cesar Hidalgo in How Information Grows talks about the concept of a person byte, which is the most one person will ever be able to know over the course of their lifetime. And it doesn't matter what that number is. It matters that it's finite, and trust me, it is smaller than the amount of information I need to understand the software system I work on. So we have to work together. We have to bring disparate knowledge together, and that's where the other bit comes in. Because the existence of multidisciplinary groups was new. That was a product of this late Renaissance. And one reason for that, one reason we had musicians and artists and poets and philosophers in the salon of the Count of Vernio was because they had just recently started to recognize art with a capital A as a thing. And this is the part that just totally blew my mind in the paper. There was a time when art wasn't a thing. People didn't know about art. That wasn't obvious then. But it's true. In the Middle Ages, like they had painters and they had musicians and stuff, but those were crafts. right alongside goldsmithing and bricklaying and putting shoes on horses. That has a name. And they organized in guilds. So if you wanted to be a painter, you joined the painting guild. And you got into the painting guild because your dad was in the painting guild, not for any particular level of talent. And that guaranteed competence. But it didn't allow for excellence, for specialization, for the recognition that maybe Michelangelo is just really that good at painting cherubs. And now you got the merchant class who can come in and actually pay for that. And so the prestige goes up, and then people recognize that there is some common thread between painting, the really good painters, and the poets, and composition, musical composition becomes a thing at all. And they don't have a name for it. I think today we would call it creativity. But back then there was like some ineffable thing. They thought it couldn't be taught, so it gained prestige. So you're sacrificing guaranteed competence. Every painter can paint a facsimile of some understanding of what you ask them to, for excellence. Not everybody has a computer science degree anymore, but we can be more creative. And that like prestige brought the artists and the painters and the poets into the salon. And it brought the painters to academies instead of just guild meetings. The painters aren't all hanging out with other painters anymore. They're talking to poets and philosophers and historians. The Renaissance was a period of decompartmentalization, breaking down barriers that kept things in order but also apart. Java developers, testers, operations. That keeps things in order, but it doesn't get much done. It doesn't have as strong an effect on the world as a team with a shared common purpose and multiple kinds of knowledge inside. Also, the new style of art in the Renaissance emphasized expressive qualities, impact on the people who see it or listen to it, over beauty of design and craftsmanship, code coverage, design patterns. Software is not a craft. And I am not a crafts person. Coding is a skill. It is a very important, high demand, super useful, essential skill for this work. A painter needs to know how to work a brush. But Java is like acrylic paint. And Ruby is watercolor. And Bash is a song on a lute. We need these. It's important to be good at them and to have skill with this. But they are not the essence of what we do. What we do is about having impact on the world. I'm also not saying that software is an art. I mean, art has an impact on the world because it has an impact on me, right? I look at a painting, I listen to a symphony, and I am changed inside, and that might change how I act in the world. Software is much more direct than that. We change physics. I pick up this box, and if I move my finger the right way, a car shows up and it takes me where I want to go. That did not happen 10 years ago. I love this world. And it took more than software. There's a lot of people involved in that, but software was essential to creating that change in the world. Software as a material is unlike anything we've been able to work with as humans before. It's more moldable than plastic. It's more malleable than metal. You can almost design right into it. And the feedback loop, I mean, we can see what it's going to look like maybe in a few minutes. And in some cases, it's only days or weeks before we can notice whether our change has an impact on people's behavior. The feedback loop is so different. I don't have to wait a generation to see whether this bridge falls down. So software is not engineering, and it's not architecture, and it's not writing. It's not any respected profession of the past. Art wasn't always obvious. It wasn't always a thing. I'm not saying that software is an art. I'm saying that software is the next thing after art. We don't have a name for it yet. The closest I can come in words is that ongoing software development is the practice of semathesy. And that makes me a semathecist in the medium of software. So I really like this slide. I know it's hard to say, but I still kind of like this word. Except there's one problem. The problem is that my name is up there. Because an idea doesn't belong to one person. It takes a camerata to build a community, to get into the culture, before an idea is real in the world. And we are all semathecists if we choose to give ourselves that title. And I am super, super lucky and happy to be alive today and in software, because software is the next thing after art. And this age is the next one after the Renaissance. We have new ways of thinking about the world, and we have new ways of changing our world and the world of our children.
If we manage to get this right, they'll surrender by early night.
The world will never be the same.
Oh, Alexander.
That's my daughter Evelyn singing Hamilton, the modern opera. May our work have that kind of impact 400 years from now. Thank you.